I started working on solar sails, gosh, I hate to admit this, 25 years ago, off and on. There's never been consistent funding to develop the technology. The work came and went depending on how successful I was at writing a proposal. And the biggest leap forward we made was probably in the couple of years before I took over the job as Chief Technology Officer. During COVID, my team wrote virtually a proposal that was us partnered with the Goddard Space Flight Center, what was Ball Aerospace, which is now part of BAE Systems, and Redwire for a nationally competed flight demonstration of a solar sail. And it was really exciting to have won that and have written a 1,000-page proposal, which includes the budget volume, I have to admit, which is probably the single largest part of it, for a $73 million flight demonstration. Now, that flight demonstration, for a variety of reasons, was put on ice a couple of years ago, but it was revived right before I left the agency. And the team at NASA Marshall is still working on it. I'll show you a bit about that today. And they've already reached out and would like me to come back and be a part of the project after the first of the year. So I'm not through with solar sails yet. So what I'd like to do is give you kind of a status update on where the world is in solar sail technology. For those that are not intimately familiar with it, I will cover just a little bit of the fundamentals of how solar sails work and how you steer them, because I think that'll give you a better understanding of why people are interested in funding it today, as it's a stepping stone for us to reach the stars someday. So, to begin, if you want to bring up my first slide, it's got all my contact info on here. I love hearing from folks. I decided to put the cover of a book that I wrote with two of the foremost experts in solar sails, Dr. Giovanni Volpetti from Italy, who has been working on solar sails probably since about the time I was born, and Greg Matloff, who was great inspiration for me and pioneer for interstellar solar sailing work. This book was published, 20 years ago, favorably received. It was reviewed in the journal Nature, and was kind of a springboard into doing a lot more work on sails. So I'm real proud of that book. Now, just to remind everybody that a solar sail is a propulsionless propulsion system. And in my entire career at NASA Marshall, which for the students that were here earlier, and I'm sorry, are you all still here? I hope you are. If not, that's fine. But I wanted you to hear this because everybody loves smoke and fire, right? I mean, you can just hear a palpable gasp in the room when they showed their static fire. Solar sails don't smoke and fire. And having worked at NASA's premier rocket center, a lot of people didn't really consider this a propulsion system. And just as a little aside, we have a whole propulsion department. And in my entire career, solar sails have never been categorized in the propulsion department. They've always been worked in the science area, and which I thought was curious because I've been trying to say this is propulsion, but there's no smoke and fire, no rocket, so it's not really mainstream propulsion. But the way it works, and I'm going to pass this around because I think people, if you haven't held this, you should. Solar sails reflect sunlight, and that reflected sunlight gives you thrust. And I'll talk a little bit about how you steer with a sail. But in the interim, Joe, could you come up here real quick? And I'm going to pass this material around. This is the actual material that has flown and will fly again in the sails I'm talking about today. This particular piece has not flown. It's 2.5 microns thick. It's a plastic. It's coated with, it's a polymer that is a polyimide that's very resistant to radiation. It doesn't get brittle very easily. It's coated with aluminum to make it reflective. And just as a quick little note, at sea level, which we're not far from here, 1 cubic inch of air weighs the same as a square inch of this sail. So that'll give you an indication of how lightweight this is, and it's pretty strong. Now, I'm going to tell you the same thing I told 5th graders at my elementary school in Ashland, Kentucky, when I gave a talk about solar sailing. You can tear this if you try. Please do not try, okay? And unfortunately, there was the one kid who tore it, and after my lecture, he came up to me with his teacher. She had made him handwrite an apology. Dear NASA, was way cool. Tears were streaming down his face. I tore your solar sail. Now, of course, I couldn't, when I got down on my knees to talk to the young man, I couldn't tell him it was okay because it wasn't okay. And what I told him was, I understand, thank you for your note. I'm glad you learned your mistake. In the future, when someone says don't do something, don't do it, right? But we'll get over this. And so he was okay with that. And I still got the letter. Not very often I get a letter addressed to Dear NASA from a 5th grader. It was kind of cool. So I'm going to pass this around and just give it back to me at the end of the lecture. So there you go. So back to the slides. So solar sails reflect light, and they derive the thrust by doing the dreaded first-year physics problem of what's the net force direction when forces are applied to something. I just remember very vividly in high school doing the inclined plane and where there are all the forces and friction. And then when you get into optics, you do the same thing. But the bottom line is when you tip and tilt the sail, you change the angle that the reflected light comes off, changes the net thrust vector, and that is critical to understanding one of the most counterintuitive things about solar sails, which I'll explain in a few minutes, which is they work better flying toward the sun than away from the sun, which is totally counterintuitive. All right, the force is very small. If you go out today on a beautiful sunny day with dry air, which we have here, and you have 2 football fields of area, the total force is roughly the same as you would experience on your hand holding a quarter and a penny. It's not much. But when you get in space and Newton's laws are at work, it will cause your spacecraft to move ever so slightly at an accelerating rate as long as the sun is shining, because F equal ma works really well in space when there's no drag and otherwise. Now, for the physics-minded in here, there was a paper written in New Scientist when I first started working on solar sails by an eminent physicist who should have known better, who claimed that these would never produce thrust. He did not know his fundamental quantum physics and the fact that light has momentum, photons have momentum. And if anybody's interested, you can do a quick calculation of how much energy is lost as a photon reflects from a sail by looking at Planck's constant and the equation shown there at the top. Now, this is kind of cool for me. Solar sails aren't a new idea. They've been around a long time. I was first made aware of them probably in the Wind from the Sun collection from Arthur C. Clarke, and again in the book, the great novel, The Mote in God's Eye, by Larry Niven and Jerry Pournelle, which was an inspiration to me. And by the way, when I met Larry Niven and Jerry Pournelle, I got them to sign my copy of that because it inspired me to work on solar sails and laser sails. But a lot of people in my generation who are a little bit older got their inspiration from reading this issue of Boy's Life magazine. I was too young when it came out, but in '63 it kind of popularized for young, at the time it was young men. I'm sure there were a few young ladies that read it, but it's also been in a lot of science fiction stories, and sails have been around in the science fiction literature for quite a while. And we have flown quite a few. Roman mentioned yesterday the flight of IKAROS, which was a Japanese mission that launched in 2010. It was a secondary payload on an interplanetary flight. They deployed it in deep space between the Earth and Venus. It was successful. It was pretty big. It was about 196 square meters, but it was really heavy. The fabric that they flew is 300 times heavier than the fabric I'm passing around here. So it was a demonstration that you could deploy a sail. It was a demonstration that it would experience acceleration, but it is not a design that even they said they'd want to use for a science mission or a mission to use that capability. NASA also flew one that very same year, but it was an Earth orbit sail, and it was a team I led, and it was called NanoSail-D, and it was 10 square meters, and it was flown from one of the little 3U CubeSats, which are small spacecraft about the size of a loaf of bread. A few years later, the Planetary Society looked at our design, made it better. We worked with the Planetary Society on that. We had a Space Act agreement, and they did a fantastic job, flew 2 Earth orbital sails at 32 square meters. I was a part of a team at the University of Surrey in the UK that flew one in 2017 called InflateSail, and the NASA Langley team led one that we participated in that's in orbit right now, and I'll show a picture in a minute. It's called the Advanced Composite Sail System. Now, the key performance parameters for each of these sails is the aerial density. And the aerial density is how much mass per unit area of the sail. And that has been a figure of merit for solar sailing for a long time, but I hate it. And the reason I hate it is it doesn't take into account everything you have to fly the sail. And one of the things that I've learned as a sail developer is you can have a really lightweight, large sail, and you can have a great metric for that, but if you don't have a way to control it during flight to balance all the forces and keep any large disturbance torques from these really long booms that deploy the sail, you'll lose control of the sail. And so I like to use something called the characteristic acceleration, which is a figure of merit for a spacecraft with a sail, which is really what you need to tell how well it performs as a propulsion system. And let me tell you why. Because force equals mass times acceleration. So if the sun is in the back of the room, and I feel like the sun is shining because those lights are really bright, and there's a certain amount of light falling on this area of the sail, there's a certain amount of force from the photon pressure. So if that force is constant, the acceleration that my sail is going to feel is dependent upon the total mass of the system, which is the sail, the control system, and the spacecraft that's attached to it. So if this is really heavy and the force is constant, the mass is high, that means the acceleration is low, and it won't get much thrust. So you want the whole system to be as lightweight as possible. So with that constant force, you get a big acceleration. And that has been the largest challenge for implementing a solar sail mission. It's not been the development of the sail, it's the weight of the whole system. For the missions that I've worked on, we have measured and tried to cut weight down to the gram level. Now that's really interesting because my colleagues in another building build rockets, and they have margins of error on their big vehicles in the metric tons, okay? And I'm worried about grams. So it makes a big difference in the sail design. And that's why the Breakthrough Starshot people were really eager to develop spacecraft that were 1 gram spacecraft on a chip, so their little sails could get big acceleration. They had to have lightweight payload mass, all right? And I think that's really hard to do. Next slide. Here we go. Let me go back one. Now, I was the PI, I am the PI, because it's still out there, of a project called Near-Earth Asteroid Scout. NEA Scout was an 86 square meter solar sail built out of that same material that we tested and retested and came up with the control systems. We did mission simulations, all the kinds of things that could fail. We had a ride to space on NASA's Space Launch System, Artemis I. We had to deliver the payload for integration to the vehicle in 2019 late because it was going to launch in the spring of 2020. It did not launch in the spring of 2020. It launched in November of 2022. The NEA Scout spacecraft was one of 10 small spacecraft that were nested at the top of the vehicle on what's called the Orion Stage Adapter, the OSA. It was a 6U CubeSat, which is like a loaf, 2 loaves of bread side by side with an 86 square meter solar sail. Had a 2-year mission plan to go to an asteroid. We had a JPL scientist who gave us an instrument. We were all ready to go. We delivered the spacecraft. It sat on the vehicle in the big VAB, Vehicle Assembly Building at KSC, for 2 years in the humidity and heat of Florida. That was not in our environmental design plan for NEA Scout. We designed these things to operate in deep space, to survive the rocket launch, and to survive about 4 to 5 weeks in ambient air as it's integrated onto a rocket. Typically, vehicles like this that experience a delay will take the spacecraft off and put it in a nitrogen atmosphere, no moisture, keeping it preserved until they can go back and reintegrate it on the vehicle. They did not do that for any of the 10 CubeSats that were on the Artemis I. I was there for the launch, went off at 2 a.m. It was gorgeous. The SLS, Artemis I, performed flawlessly. Our spacecraft did not. It never called home. And of the 9 spacecraft, of the 10 that were on the vehicle, only 1 completed its mission successfully. We had a meeting afterwards to come to root cause analysis, and we all kind of decided each of us experienced a different failure, but we all traced it back to sitting on the vehicle for over 2 years without being put in a nitrogen purge. That was a huge disappointment to our team. We had spent 7 years working on this payload, among other things. I had other things to do at the time, but 7 years. But we learned a lot, and we capitalized on that. And in parallel, there was an effort at NASA Langley to take essentially the same size sail, but instead of using metallic booms, to develop composite booms, which are lighter weight. And they recently launched in 2024 a mission called ACS-3, the Advanced Composite Sail System, into Earth orbit, another Earth orbit deployment demonstration. They successfully deployed the sail with one glitch. They have one of their composite booms has a bend in it. And so the sail is not fully square and symmetrical. Now you ask, why is that a problem? It's a huge problem. Because if you don't have a fairly flat sail, you have differential thrust on one side of the sail versus the other side of the sail relative to the center of mass of the system. If you know anything about torque, for example, why you put the handle of a door opposite the hinge, then you understand the problem. The problem is these booms are really long. And if you have more solar pressure here than you have here, it's going to tend to want to push the sail over like this. And you have to have some kind of countervailing force to keep it flat. That problem for ACS-3 has not been fully resolved, and they are in Earth orbit, and with the government shutdown right now, the whole system is basically in keep alive mode until the team gets back in there and works on regaining and doing the attitude control. So the lesson learned from that is we have to be really careful, do a little bit of over-designing to prevent that kind of boom bending. Otherwise, it was a successful deployment. They just haven't been able to do all the mission operations they want to do yet. Also in orbit is a project that I started several years ago. I was a co-investigator on it because I was really busy working on the NEA Scout, and a really sharp physicist from Iowa who came to NASA started working on this called the LISA-T. It's called the Lightweight Solar Array and Antenna. And here it looks just like a typical spacecraft with a solar panel, but when you look closely at it, it's in orbit right now, those are not solar panels. Those are miniature solar sail wings. And integrated on those and adhesively bonded are thin film photovoltaics, which are barely heavier than that solar sail I passed around. They're not very efficient. They're under 20% efficiency, but you can pack a lot of area in an extremely small volume for very low mass, and for short-lived missions, i.e. a couple of years in Earth orbit or beyond, there is no solar array that'll beat it in terms of mass per volume or power per volume for launch. It has been demonstrated with the LISA-T in orbit, and as usual, there are glitches. There was a glitch with the deployment of 2 of the wings, but it has generated power. It's now shut down, as was planned. The one thing that we had hoped to do but were unable to do that relates to interstellar travel is 2 of these wings produced power at 1064 nanometers. What's significant about 1064 nanometers? Lasers will traverse the atmosphere pretty well at 1064 nanometers. We had an agreement with an aerospace company that shall be unnamed at this point to shine a 60 kilowatt laser from the ground onto the LISA-T pedals to demonstrate the longest ranged beam power demonstration that anyone's ever done. Before I left the agency, the contract was going to expire with the spacecraft operator for this, and the aerospace company that I shall not name had a break in their laser and were unable to get the laser repaired to do the experiment before the mission was shut down. So very, very disappointing. To the best of my knowledge, that laser is still not working. It had been working, but when we needed it, it wasn't available. So I think that experiment will come back. There are a lot of people working on beam power, a whole topic of a different presentation, but there's a lot of work going on in beam power today. So this is exciting because, quite frankly, this is a potential alternative in the future to RTGs for outer solar system exploration. We did a mission study that said basically if you take the Near-Earth Asteroid Scout solar sail, 86 square meters, cover it with this photovoltaic, you can use it at Uranus and Neptune instead of a plutonium power pack, because you can generate enough power that far away from the sun with this very large solar array So there are a lot of applications for sail technology as we go toward the stars that'll be beneficial to solar system exploration. So I'm really excited about that demo. Now, you're here because you want to hear about interstellar travel. Well, as you know, we've looked at solar sails for reaching the stars. This is a graphic that came from the PI, University of, I think he's at UCLA, Artur Devoyan, who I worked with on a rapid solar system escape concept proposal, which is basically taking very healthy substrates that are heavier and more reliable than the substrate I'm passing around here, that could take a spacecraft inside the orbit of Mercury to deploy the sail there to go out of the solar system at very high velocities. For those of you that are not intimately remembering your optics from college or never had it, real quick lesson as to why this is important. Again, the sun is back here. It's kind of interesting. It's a binary star. We're at Alpha Centauri, getting too much light. As you take your sail, you have a certain amount of light that falls on the area of the sail. If I to take this and double the distance from the light source, I don't get half the light on the sail. I get 1/4 the amount of light. It's called the inverse square law. If I take it to 3 times the distance, it really drops rapidly. It's no longer 1/4. It's 1/3 times 3 times 3. So it really drops rapidly. But if you go toward the sun, and I take the distance to halfway from me to the sun, I don't double the amount of light. I get 4 times the amount of light. If I go to 1/4 that distance, Mercury distance, I get 16 times the thrust. So if you have a lightweight sail system and you deploy it close to the sun, you get a lot of sunlight pressure. With a very large sail, something, say a square kilometer, deployed inside the orbit of Mercury, you can get a lot of kick and go really fast to exit the solar system. He was looking at various new materials that came along after the development of graphene, which I talked about last night, which could survive the environment close to the sun and the forces on the sail to do rapid solar system escape. That study did not make it to phase 2. I think it's going to be reproposed. I'm hopeful to be on the team and continue to work on that with some of these new nano 2D materials that are engineered. So the sails we eventually need, in my opinion, separate from what Breakthrough Starshot was working, I think we need 1 square kilometer sails that are 1 atom layer thick. Right now, I would build them out of graphene with some kind of a coating like aluminum to go very close to the sun. They need to have a very small aerial density, very low mass spacecraft. I think that we could probably build some of these on Earth and launch them. It's questionable whether we'll have the ability to build these things in space anytime soon. I would hope that we do. They're currently much bigger than what we have today. I think there is a path to making them. I'll talk a little bit about that in a few minutes. But this is what we need. This is the kind of scale that we need ultimately for an interstellar voyage. Now, I promised to give you an update on the mission that was called Solar Cruiser, which is the one that I led the team and we won during COVID. There's always an interesting story that goes along with these things. I'm going to take a brief aside here to tell you the travails of working during COVID, as if some of you all didn't have this experience in your own way. These science missions are extremely competitive. And the final decision was made as to who was selected by the director of NASA's Science Mission Directorate. At the time, it was a fellow named Dr. Thomas Zurbuchen. Some of you may know Dr. Zurbuchen. And it was a final design competition between us at the NASA Marshall Center and a team at the Goddard Space Flight Center who had a totally different technology they wanted to demonstrate on the flight. We had passed all the peer reviews. We were the 2 top teams out of about 10 teams from across the country that had competed, most led by non-NASA people. It just so happened in this case 2 NASA PIs were going head-to-head on this one. And we were giving this presentation remotely to Dr. Zurbuchen, who was at his home, wherever that was. And we were told the fairness of this would be essential. You would have 20 minutes with 10 minutes for questions, starting at this time and ending at that time. And if there were any technical glitches, the clock kept ticking. Too bad. So I'm home, I'm at my desk, got the red flag on the door, so my family is not going to come in and knock on the door while I'm on this call. They were extremely good during this time. I have to give a call out to my wife and daughter as we were writing this proposal, and I was working till 9 and 10 and 11 o'clock at night. Food came, drink came, it was great. I thank them profusely for that, kept me going. So I'm on the line with Dr. Zurbuchen. I've got my computer here. It's my turn to present. Slide 1 comes up. Slide 2, my computer turns into a brick. Totally dies. I have no idea what happened. The whole power went out. It's like, oh my gosh. So I'm sitting there. I have my cell phone. I have 2 other team members on the line. I know my charts. So I called one of my teammates, and they said, Les, what happened to you? You're not on the line. They're all waiting. And I told him, my computer brick, do you have my slides? He said, yes. I said, display them, put me on speakerphone, and put my phone on your microphone on your computer. I didn't have my slides in front of me, but I knew my material. And as I went out, my colleague read the title slide, and I talked to the slide from memory. Got to the end of the presentation, found out the next morning we won. Okay? I think partly we won because that worked in my favor, because it showed we had a disaster at a critical moment, and the team got together and we got through it. And so that was one of those, oh my God, we're dead moments that I think actually helped us win. So that's why I wish the students were here. Sometimes you got to figure out how to turn adversity into a win, right? And I think that was part of the reason we won that competition. But the mission is to take a 1,600 square meter sail. You don't think in metric usually. I typically don't. 17,800 square feet, okay? Basically the size of Walgreens floor, okay? Made out of that material, deployed by 4 booms, each 100 feet long, to L1, Sun-Earth L1, fly a little bit sunward of L1 using solar radiation pressure, and as the Earth orbits the sun, always remain between the Earth and the sun as we're going around the sun. And the reason for that is because the science community wants to better understand solar storms and give advanced warning for solar storms before they reach the Earth. So we have a lot of interest from NOAA, the weather people, because they're responsible for space weather forecasts as well as terrestrial weather forecasts. And if you don't know what that means, go look at space weather and you'll find out. We get bombarded by radiation from the sun all the time. And when a bad storm comes along as a result of a coronal mass ejection on the sun, spacecraft have to batten down the hatches, power down some systems. It can cause power blackouts on Earth, and has. Our colleagues in Canada know that. Were you up there in the Montreal blackout? You were, yeah. So there was a power outage caused by a solar storm because it caused problems with the transmission lines and the transmission of power at high latitudes, and it can be much worse than that. Just look up the Carrington event. So hopefully, yeah, Stephen. Currently, there are spacecraft at Sun-Earth L1 that provide the advanced warning of solar storms. And how they do that is they're far enough out that when the storm hits, which is mostly protons, which are traveling pretty fast but slower than the speed of light, the detectors say there's a storm coming and they radio a transmission. And we have about 15 to 20 minutes warning to batten down the hatches. The solar sail, solar cruiser class, will fly sunward of L1 and double the warning time, okay? That's significant. And it's something that'll also be significant when we're sending astronauts back to the moon and onto Mars, because if you look up your space history, one of the Apollo missions, I forget which one it is now, missed a major solar storm by about a week. And it could have been a very, I don't know if it would have killed them, but it would have made them very ill because they were basically totally exposed to that radiation. And so they did not get it because the solar storm didn't happen while they were on the way. But mission planners for moon missions and otherwise, and if anybody watched For All Mankind, any For All Mankind fans in here? Yeah. You remember the episode where they had the solar storm? Yeah, with the European astronaut and all that. That's real. And that they have to take shelter when those storms are coming, and this kind of capability would double the warning time. So that would give astronauts, 30 minutes warning instead of 15. Take shelter or die kind of thing, right? So that's a big deal. And so they're really interested in flying that. So Solar Cruiser, just for those who want to know the inside story as to why we weren't confirmed and why we aren't launching this year as we originally planned to launch, is because our budget was limited and this mass thing came back to bite us. We couldn't afford a custom-designed lightweight spacecraft. All we had budget for was a commercial off-the-shelf spacecraft on somebody's production line, a company that shall not be mentioned, who had a production line of small spacecraft they sell to other people to use. Between the time we wrote the proposal and selected, you know, things improved and changed. They changed some of the design features of their commercial off-the-shelf bus with an improved onboard thruster for attitude control. No big deal. We're just upgrading what we have. Except they hadn't finished all the qualification testing to make sure the upgrade worked. And right before we had our confirmation review, it failed. And the company, that again shall not be named, but I'll tell you in a side conversation when I'm not being recorded, said, look, we're sorry, but our thruster did not pass qualification. It's going to take us an extra 5 to 6 months to do the whole series of qualification tests again. That hit my schedule 3 months beyond our reserves. So we no longer had schedule to fly. It was not the sail. We were not confirmed for the flight they had given us. They gave us an extra $12 million to complete the sales system to flight readiness, which in NASA parlance is technology readiness level 6, which we've subsequently done, and I'll show you a picture now. And we had to wait for another flight opportunity. There are not a lot of launch opportunities to go out of Earth's orbit to the sun. Just saying, right? And we couldn't afford a dedicated launch, so we have to ride with someone else who's already doing that. Well, it turns out there's another opportunity in 2029 that was made available to the team. And there's funding flowing now to restart the project with a different spacecraft provider and fly to Sun-Earth L1 in 2029. This was all announced right before I left in my retirement, okay? So I feel pretty good. We got it in place. Now it's going to go, right? So the team was working on that till the furlough hit. So I don't know how that's going to affect schedule. So I'm going to show you some pictures of the sail system. I showed a little bit of this last night. The sail is deployed by 4 booms that are graphite composite that are 29.5 meters long each. Each is about 100 feet long. Get your arms wrapped around that. Looks like measuring tape. You know how measuring tape's metal and it deploys and it kind of bows a little bit to keep it rigid? That's exactly what this does. It's called a track boom. So it coils up really compactly, and when it's pushed out with a motor, it deploys and becomes rigid as it goes out. This is a picture here of the fabrication facility in Huntsville where these sails are manufactured. It's a company called Mantech Nexolve, and they make the sails in a clean room, and they're the same company that made the sunshade for the James Webb Space Telescope. Okay, so that's the heritage of the folks working on it. This is one of our deployment tests. The sail's made in quadrants, 4 equal design quadrants. This is one that we tested at NASA Marshall that's 1/4 of that 17,800 square feet, and that's me on the back wall, 3rd from the right, after we did a full-scale test. Now this is fun. This is the video of the deployment, and I'll ask him to play it twice because I'm going to talk to it as you play. Go ahead and hit play. This was a test out at Redwire in Longmont, Colorado, that we did about 1.5 years ago. The pink is an anti-static coating that had to go on the floor because we couldn't support the weight of the sail any other way except basically deploying it on the floor. These are the deployment of all 4 100-foot-long booms, only 2 of which are going to go to full-length deployment to deploy the quadrant of the sail. The other 2 booms are going onto a take-up spool. But all of the sail will fit on that spool that you saw, but we only had 1/4 of it on that spool. And you can see it coming off right there and as the booms are going out. And that is the same material that's being passed around the room. We had 1 minor tear, not a big deal, in the deployment. So the sail, after that, we've had it through thermal vac testing, we've had it through the acceleration shock testing, vibration testing, long duration space environmental effects testing. Of course, they have to have the candid shot of the PI and the project manager in there when they do their video. And that's the team that was there for the deployment. Play that again so people can get a sense of what that looked like. when it comes back up. And the company is Redwire. A lot of people say, well, you know, NASA does this and NASA does that. We work with contractors. This is commercially developed to our specifications, and they worked with some of the NASA folks to make that happen. It was really interesting working and coming up ways to do gravity offload, because the harshest environment a sail will experience is being manufactured and tested on the ground. The second worst environment a sail will experience is during launch and all the vibration and going to space. And the space environment is actually the easiest environment it has to operate in and the least likely to be damaged. So we're real thrilled with this, and the project is moving forward again. There's a Delta PDR preliminary design review planned was next spring. I suspect with the shutdown, it might now be next summer. So it's moving forward, which I'm really thrilled. Yes, can you come to a microphone if we have questions? But let's wait until I get finished, if you don't mind. Let me run through everything. So going to the next slide, there's that picture again. I love the picture. I showed this last night at the outreach event, but now you get a really sense of the scale of things. You've heard about some of the sails, the near Earth, there's the NanoSail-D, 10 square meters. There's the NEA Scout sail and the ACS-3 sail at almost 100 square meters. Coming down here at the bottom will be the little Lisa T with its photovoltaics, which is a spinoff of the technology we developed for NEA Scout. And comparative size is Solar Cruiser, now called S5. And it escapes me what, oh, there we go. Space Storm Solar Sail Sentinel. I hate the name. I wasn't naming it, so I didn't get to try to give it a cool name like Sundiver or something, which I wanted to do, but they gave it a nice NASA acronym instead. So that's it. The project is reborn. It's moving toward flight, and I'm super pumped. I'll be working on it again after the first of the year, assuming it survives the shutdown. It is also something, there's another community that you all need to be aware of, and actually IRG was very, very gracious and allowed me to attend a meeting at the United Nations that was held about 2 months ago, where a team of folks looking at this went and briefed, not to the whole General Assembly, but to a subset of nations for something that a lot of interest is being generated for as a possible tool in the toolbox to help combat climate change. And that is taking the same scale sails that we need for interstellar travel and deploying a whole lot of them at Sun-Earth L1 to actually block some of the incident sunlight coming toward the Earth so that we don't have as much heat coming into the atmosphere as we're trapping more heat with carbon. It's called a planetary sunshade, and this community is extremely interested, just like the sail for interstellar travel community is interested, in having this capability and putting it in the toolbox of nations and folks to consider as a climate change mitigation option. What they want to do is put the sail at a location so that we're not in a shadow like an eclipse. The umbra of the blocked light would fall somewhere in space between the Earth and L1, but we'd be in what's called the penumbra, which is a shadowed region, but it's not like a blackout like you experience during a total eclipse. And if you deploy enough of these there, you can offset a few degrees C of the Earth's heating. So this group has big ambitions. They need the same technology, are really big advocates for this. I'll be talking more about the meeting at the UN and where this group is going in a possible solar sail race that they want to use to incentivize the development of the technology. And it's sponsored by some very capable, resourced people. And I'm on the planning team helping them come up with a definition of what this race will be called, which is the Earth Cup. And if you Google Earth Cup, they now have a website that's out there. And I'm going to encourage, no matter what you think about climate change, I don't want to get into that debate, they are people who are advocating for the same technology we're advocating for, of the same scale that we're advocating for. And I can see a fantastic roadmap of the groups working together to develop this capability, to develop these sails. And oh, by the way, in parallel, as we'll talk about in a minute with beamed energy sails, there are a lot of companies now working on space solar power, some of them using lasers. There's a company, I've forgotten the name of it, Ethereum or Etherflux, I think it is, that are developing a optical power beaming that could be used with sails to accelerate them to high speeds and could also be used to generate power with space solar power. So I have this visions of the science fictional future where we have these power beaming stations beaming power down to the Earth, and when we launch sails, they divert the beam and accelerate the sail out of the solar system. And Tony, I just felt a story coming on. But anyway, so I think there's a lot of synergy going on right now in the advanced space technology community, which I would love to talk to you all about, because I think these three communities could converge to enable our vision of interstellar travel a lot sooner than it would have otherwise, because all these things are starting to happen now. Power beaming, sunshades, solar sails for solar sail race and for science and for interstellar travel. So it's pretty exciting. Just in case there are people who are worried, there is an example of what one of these sails might do. We had, a Venus transit. This is a picture of Venus transiting the sun superimposed with how big this sunshade would have to be, which sounds science fictional, and it kind of is. But you know me, I'm not shy about dreaming about big things, and neither is this group. So we want to talk about that and maybe really, really big sunshades, and I need to learn how to spell Earth when I do this slide again. So I want to get to this chart. I showed this last night because this is really important to me. I drew this map up 20 years ago, and I found out there's a version of it in the British Science Museum, which is so cool. I had somebody send a picture of it to me from the UK. It's got a little attribution down there, NASA. Thank you very much. But I created this, and it was basically saying, we need to start small with this 10 square meter sail, build a 100 square meter sail, which we did with NEA Scout and ACS-3. Then we need to go to 1,000 square meters, order of magnitude every time. Solar cruiser. I need to be quiet. That's what it sounds like. He told me he had more time to talk. But anyway, we're eventually going to get up to the very large sail and go to the stars. I just want to conclude by saying that Dr. Robert Forward, great visionary, wrote a lot about beamed energy sails. Beamed energy is coming along rapidly. Been a lot of tests with microwaves and with lasers. We're going to build these, I think, in the not too distant future, not to starshot scale, but a more manageable, evolvable scale. I want to mention also to this community that there's going to be a special issue of Breakthrough Propulsion for Spacecraft, which I'm co-editing with Martin Tajmar in Europe. And we'd love to have contributions to this. If you're interested, use this QR code or see me later. We're looking for papers for this special edition. It'll be a peer-reviewed journal publication of Breakthrough Propulsion for Spacecraft. And I want to close, and if I have time for any questions, take those now while I do my blatant commercial message in terms of buy my books. I'm no longer employed by NASA and like to sell more books. So thank you.
Hi, Les. Great presentation, but I wanted to focus on the kid who tore your sail. And
The what toward my sail?
The kid who tore your sail.
Oh, yeah.
I spent a great deal of my life as a quality assurance analyst and a quality assurance manager, and I think this kid's got potential. What we need to do is to turn his destructive criminal tendencies for good.
Well, that's why I couldn't tell him it was okay. But I did try to make him feel better after he'd done that. So you're right. We need good people who will test things to destruction.
My sister refers to me to her computer science students as her brother who lives on the dark side.
Yeah, there you go. There you go. Mad scientists unite. I got that. That ought to be a new union label. So, all right. Well, thank you all very much. See you all later.